colloids are kind of like solutions, but they are different. In a colloid or a colloidal dispersion, the solute, what you would think of as a solute, is finely divided and it's dispersed. Those particles are small enough that they will stay suspended in the liquid, but they are larger than typical solute molecules. So they're typically like 1 nanometer to 1,000 nanometers in diameter. And that gives these mixtures some different properties. I'm going to skip ahead. The Tyndall effect. So the Tyndall effect is that when you shine a bright light through a colloidal dispersion, you can see the beam of light. And the reason for that is those particles are large enough that they can scatter the light. This solution is still transparent. You can see through it, but a strong beam of light gets scattered. This is a solution, same beam of light going through there, you can't see it. This is another example of the Tyndall effect. So here we have this great hall, and there's some dust in the air, and the sun comes shining through the windows, and you can see the sunbeams. Well, the sunbeams are going to be there whether you can see them or not. The reason you can see them is because it's dusty in here. So the fog is an example of, we had some of that yesterday. Yeah, up here. Fog is a type of a dispersion, a colloidal dispersion, where we have water droplets in the air. And the water droplets are large enough that they mess with the light. They diffract it, they reflect it, and so you shine your headlights in the dark, in the fog, and it just lights up the fog, and it doesn't help you to see because the particles are bigger. Their water droplets are larger. Now, normally there is water in the air, but it's individual water molecules, and those are too small to reflect or diffract the light. Other examples, smoke. We've had a lot of experience with that. Whipped cream. We had that at Thanksgiving, hopefully. Milk is a suspension. It's called an emulsion, where you have milk fat globules and proteins in water, and then a solid emulsion, a liquid in a solid. An example of that is an opal, and that is created by water being suspended in glass. Okay, so let's go back. Now let's do this one first. So soap can form a colloid, and we could represent them as these little guys right here. So here's a soap molecule. We showed these earlier. One end of this is very polar. It's actually an ionic end here, and then this is nonpolar. So you stick this in the water, and these nonpolar tails tend to cluster up, and they'll put their polar heads to the outside to interact with the water. And they'll form these micelles, and those are small enough that they will stay suspended in the water. So you put, dishwashing soap in the sink, and you swish it around, and you come back later. The soap hasn't all fallen to the bottom. It's still suspended because it forms these little micelles. The micelles are separated from each other. They keep from just clumping together into a big glob because of electrostatic repulsions. There's negative charges on the outside of this, and so this one is repelled from that one, and so they will stay separated. Other large molecules, such as proteins, will also form colloids. If we look at colloidal particles under a microscope, they have a distinctive jittery motion, and that's called Brownian motion. It's caused by collisions of the collisions of the dispersed particles with molecules in the liquid. So I've got this video. It's not very long. See how they look like they're alive, but they're not. Not this one. It's a cool video, but we're not watching that right now. So this was named after the guy who discovered it. His last name was Brown. It's a bit like a beach ball at a graduation or some big event in a stadium. They throw beach balls out and everybody just kind of hits the ball. It just kind of goes all over the place. The colloid particles are like the beach ball, and the people hitting them are like the water molecules. So this gives evidence that water molecules are moving, even in a still sample of water. The water molecules are moving. And we can see the effect of that when they hit these colloidal particles. The colloidal particles are large enough that you can see them under a microscope. You can't see water molecules.